This lab discussion is on the hydrolysis of salts and buffer solutions. Salt solutions can be classified by the relative strength of the acid and space of the salt. Acidic salts are comprised from a strong conjugate acid of a weak base and a weak conjugate base of a strong acid. pH is less than 7. Examples include NH4Br and CH3NH3I. Neutral salts are comprised from a weak conjugate acid of a strong base and a weak conjugate base of a strong acid. pH is approximately 7. Examples include BaCl2 and LiNO3. Basic salts are comprised from a weak conjugate acid of a strong base and a strong conjugate base of weak acid. pH is greater than 7. Examples include NaF and LiCN. View the video below to further understand how one can learn more on the properties of salt solutions. Another topic to discuss is on buffer solutions. Buffer solutions consist of either a weak acid and its conjugate base or a weak base and its conjugate acid. The main purpose is to resist pH change by the addition of acid or base. Review any of the videos below in understanding buffer solutions or performing buffer solution calculations. In respect to pH calculations, if you have a buffer solution, one can calculate the pH of these solutions using the Henderson-Hasselbalch equation, where pH equals pK plus log of the ratio between base concentration over acid concentration. Remember that pK equals the negative log of Ka. The objectives of this lab include the following. 1. Understand the concept of hydrolysis. 2. Be familiarized with acid-base indicators. 3. Understand the behavior of buffer solutions. Part 1 of this lab is on indicator analysis. You need test tubes to, with the aid of indicators, determine the pH of each salt performed. Record the color of each of the following indicators when added to boiled water, unboiled water, along with 0.1 molar solutions of ZnCl2, NH4Cl, KAl, SO4 parentheses 2, Na2Cl3, NaCl, and NaC2H3O2. Indicators are methyl red, methyl orange, bromothionyl blue, phenol red, phenolphthalein, and alizarin yellow are. Determine the approximate pH of each of these salt solutions, including water, based on the color of the solution and pH per indicator. Part 2 of this lab is on studying a buffer and non-buffer solution. Lab questions used where, with the aid of a pH meter and buffer solutions seen below, determine the pH of various aqueous solution mixtures. Calibration of the device must be performed. In lab, you will be provided pH 4 and 7 buffer solutions, and videos for how to do a 2-point calibration is provided. The pH electrode must be stored in one of the buffer solutions to ensure it is not dry when not in use. Dry with Kim wipes, not paper towels. You will be making a non-buffer solution between 30 milliliters of water and 1 milliliter of 3 molar HCl and 1 milliliter of 3 molar NaOH in separate beakers. My recorded video is done with 1 milliliter of 6 molar HCl and 1 milliliter of 6 molar NaOH. In another set, you will need to prepare a mixture between about 3.5 grams of sodium acetate trihydrate and 8.8 milliliters of 6 molar acetic acid in with about 56 milliliters of DI water. You will need to perform calculations as to what the expected pH is from the molarities of water is with additional HCl and additional NaOH. In addition, determine the pH of the buffer solution from the given amounts, and along with that, the pH of the buffer solution is after adding 1 milliliter of 3 molar HCl and adding 1 milliliter of 3 molar NaOH. Note, pH of the neutral water solution is 7, assuming T equals 25 C. Show calculating for this pH with Kw. You need the equations shown below, dilution equation, or stoichiometry to solve for the final concentrations of the acetic acid and acetate ion after the addition of acid and base separately. Think of what errors could there be if you are doing this lab in explaining the differences in pH. When working for calculating the pH of a non-buffer solution, water with either the addition of excess acid or base, using the formulas below to calculate the final molarity of both H2O plus and OH minus. Afterwards, solve for the pH of each solution by taking the negative log of H2O plus or alternative equations to eventually get the pH of the solution by the addition of H2O plus or OH minus solution in water. In working with a buffer solution, if you have excess acid present in terms of H2 plus or H plus, use the formulas below to find the equilibrium concentrations of HA and A minus. If either HA equilibrium or A minus equilibrium is a negative number, the buffer is destroyed. In this case, you will have to use the Rice table to solve for the eventual pH of the solution. If you have excess H2O plus, you can directly calculate the pH of this solution. Perform a similar approach if you have excess base present in terms of OH minus. If either HA equilibrium or A minus equilibrium is a negative number, the buffer is destroyed. In this case, you will have to use the Rice table to solve for the eventual pH of the solution. If you have excess OH minus, you can directly calculate the pH OH of this solution, followed by the pH of the solution. Some final comments include the fact that this lab requires you understanding solving equilibrium problems for acid-base salts, and buffer solutions. You need to understand solving the final concentrations of any aqueous substance using stoichiometry calculation and or Henderson-Hasselbalch and or Rice table analysis with equilibrium expressions and their respective concentrations. If you have any questions, please ask your instructor. Enjoy the lab.